Hi there, welcome to this video for AP Calculus. We're going to talk about area between curves. This is lesson 8.4 for my class, and we are going to find the area between two curves. The integral from a to b of f of x dx produces a value or assigned area, which may be positive, negative if it's below the x-axis, or 0. However, what if I'm asked to find an actual area of a specific region? It's important to note that this area cannot be negative, and we'll kind of elaborate here. What about the area of a region between two curves? Well, an area between two curves can easily be found if I take the area of my upper curve, right? That would be the integral here of f of x from a to b. And what I'm going to do is I want to subtract this area underneath my lower function. So I'm going to subtract the area below my lower function. And so what you can see, in order to get this region, I'm going to subtract this overlapping region, which is the area under g of x, okay, with respect to the x-axis in front of these bounds. So here is the area between two curves. It is the integral from a to b of f of x minus g of x. Man, this thing does not like me. Okay, f of x. Come on, let me highlight. There we go. Sorry, the integral from a to b of f of x minus g of x dx. If f and g are continuous and f of x is always bigger than g of x or equal to on that interval a to b, okay? So plain and simple, for functions of x, area is going to be equal to the integral of the top curve minus the bottom curve with respect to x, where your bounds a and b are in terms of x. And sometimes we see cases where our functions are in terms of y. We're going to use the same kind of idea, but we'll use the right curve minus the left curve, okay, with respect to y. So let's go ahead and let's kind of see an example of it. Here's an example. They say, find the area of the region bounded by y equals x squared plus 2. Okay, that's a parabola shifted up to. We can see this curve right here. And y equals x. Okay, this is a linear function. We can go ahead and see this curve right here. X equals 0. So now they're giving us some vertical lines. That's this line right here. And x equals 1, which is this curve right here. Okay, and so we want the area enclosed in here. So using this idea of what we just did, area is going to be equal to the integral from our lower bound is 0 and our upper bound is 1. Our top curve here is the x squared plus 2. Sometimes I like to put that in parentheses. It's more important for our right function, what we're subtracting. I'm going to subtract x here, especially if I have multiple terms. Okay, that's going to be very, very important here. So dx, and I'll put parentheses around all of that. So that is your area setup. In FRQ that can have this type of question, sometimes they just want you to set it up. This is pretty straightforward. So let's go ahead and kind of clean all of this up. This is x squared minus x plus 2 dx. And we can easily find an integral of this, right? We have 1/3 x cubed minus 2... minus x squared over 2 plus 2x, evaluated from 0 to 1, okay? And we can plug in our upper bound, and we get 1/3 times 1 cubed, which is just 1, minus 1 squared divided by 2, which is just 1/2, plus 2 times 1, which is just 2. Again, minus, now I have all this, and I'm going to subtract all of this. So I have 1/3 times 0 cubed minus 0 squared over 2 plus 2 times 0. And I know, again, all of this goes to 0. This is what we call trivial. It'll all disappear. But what if it does not? What if it does not? Sometimes we have some terms in there that don't. So this one does. But the other thing I want to point out, just be careful, especially when you're subtracting and you have multiple terms in your, answer here. You want to make sure you put parentheses around it because you're taking away all of them. Okay, so there you go. There is our area. All right, sometimes you're going to have to find where two curves intersect to determine boundaries for your regions. These intersections will provide you with the limits of integration for your integrals. You must show the equation setup, even when using a calculator to find the intersection. So this is very important here. And two, on this one, it looks like we can go ahead and identify them. What's important is that we show the setup, and we'll do that here. Find the area bounded by the curves F and G. Okay, so this is going to be equal to, man, why is this thing tweaking out today, guys? It does not like me today. What is that? Okay, this is going to be equal to the area is equal to, and we want, oh, well, first of all, which one is which? That's important. I have these two functions. I have f, that's a quadratic, so we can kind of see this here. Here's our quadratic function. It looks like that one's on the bottom, guys. So I almost went f minus g, but in our situation here, it looks like our linear, looks like our linear function's on top. There's g of x. Okay, so this is going to be g of x minus f of x. Top minus bottom always. Okay, so d of x. Now, I don't have my bounds. I got to find my bounds, and so what we'll do is we will set f of x, which is x squared plus 2x plus 1, and we'll set it equal to g of x. And g of x is 2x plus 5. So set them equal. Sometimes you have to go ahead and find them. We can easily, find them here by moving everything over to one side. And if I do that, if I subtract 2x and I subtract 5, looks like those cancel. We get x squared minus 4, which gives us x squared equal to 4. So x is equal to plus or minus 2. And visually, that's kind of what happens. Make sure you always set the bounds equal to each other if they do not tell you. Okay, so at least write that equation statement equal to each other. So we go from -2 to 2. Okay, so let's go ahead and find this answer. So -2 to 2. Again, g of x is x squared plus 2x plus 1. And then minus f of x, which is 2x plus 5. Okay, all of this dx. So, and actually, this is going to look very familiar. I'm going to subtract 2x, I'm going to subtract 5, and what we end up with is the integral from -2 to 2 of x squared minus 4 dx. And I can go ahead and evaluate this. So I get, I don't need my symbol, because I'm evaluating x cubed divided by 3 minus 4x, evaluated from 2 to -2, okay? So here, definitely make sure you mind your parentheses. 2 cubed divided by 3 minus 4 times 2 minus, and I'm going to put this in big parentheses here, we have -2 cubed, put that in parentheses, minus 4 times -2. And there is your answer. Okay? So, area between two curves, top minus bottom, very, very important. Okay? Here's example 3. I would like you to go ahead and pause me. I want you to try this example, and then we can check your work. Okay? So pause me. Try this one. Okay, here you go. This is what you should have gotten. The integral from 0 to 3 of -x cubed plus 4x plus 2 minus x plus 2 dx. The bounds are found by setting them equal to each other here. I moved everything over to the right side to get a positive quadratic, which is x squared minus 3x. I factored a GCF of x out, and we got zeros of 0 and 3, which you can easily see given the graph, but if you didn't have the graph, you'd have to find those. And then we're going to go ahead and integrate here. -x cubed divided by 3 plus 3x squared divided by 2. And we can go ahead and plug in those bounds, and there is your answer. Okay, so the next thing that I want to go ahead and show you are kind of two unique cases for these types of problems. The first one is functions of y. Sometimes we are asked to integrate with respect to the y-axis, or our functions are laid out in such ways that I don't really have a top minus a bottom, but I have like a right versus a left. And so I'll go ahead and show you that here. Our first one here, this is x equals y squared minus 3. So I am left 3, and then I have a quadratic function here. And so I can quickly go ahead and graph this quadratic function. Okay, as such. And then we have a linear function. So I'm shifted up 1 with a slope of 1. And there are our two functions. And so this is the area that they want. They want this region. And so note, in this case, I don't always have, one function that is on top of another function. I do have a right function and a left function. This function is always to the right of this function. So I'm going to go ahead and integrate this with respect to y. Now my function here in blue, the parabola is already in terms of y, but I need to go ahead and I need to take this and put this in terms of y, or x equals. So if I just subtract 1 on both sides, we get y minus 1. Y minus 1. So here's going to be the area. The area is going to be equal to the integral of right minus left. My right function is y minus 1. My left function is y squared minus 3. Okay, dy. And so I'll put parentheses around all of this. The thing that's missing are my bounds. And so what I'm going to have to do, and again, it looks here, it's like it's going to be, well, here's the other thing, is that your bounds, this is in terms of y, this needs to be y equals certain values, right? So it's not going to be right and left x values, it's going to be up and down y values. So it looks like it'll be -1 to 2, but let's just go ahead and see. So if I have y squared minus 3, and I set this equal to y minus 1, I can go ahead and move everything over to the right. So I'll minus a y, add a 1, which gives me a minus 2, and I have a parabola. So y minus 2, y plus 1, and these are our bounds. So I get y equals 2 and -1, which is what we thought. So -1 and 2. Okay. So anyway, that's kind of how you do a setup for in terms of y. Put everything in terms of y, just like u substitution, where everything had to be in terms of u. If you're going to do functions in terms of y, right minus left, your bounds also need to be in terms of y, as well as your dy here. Okay. So bringing this one all the way home, the integral from -1 to 2 of, it looks like -y squared plus a y, it's going to be a plus 3 minus 1, so plus 2 dy, just the flip of what we just found. And then here is our integration, -y cubed divided by 3 plus y squared divided by 2 plus 2y, evaluated from 2 to -1, and we can go ahead and plug these in. So -2 cubed divided by 3 plus 2 squared divided by 2 plus 2 times 2 minus, and I'll put all of this in parentheses here, -1 cubed over 3 plus -1 squared over 2 plus 2 times -1. Okay, and there is your area for that value. Okay, all right, so that's a kind of a weird case with these problems. The other kind of weird or unique case with these types of problems is when I have something that looks like this. The graph of f of x equals square root of x, and g of x is equal to -1/2 x plus 4. Determine the area enclosed by these graphs in the x-axis. So this might seem initially kind of like a area between two curves, but really it's kind of like these graphs and the x-axis. And so really what I kind of want you to see here, and I guess you could set this up in terms of y, like right minus left, right minus left, but you'd have to convert both of these in terms of y and do that. But I kind of want to see also here, you to see that I could split this. If I go ahead and kind of put this intersection here, so area under this first curve here, okay, and then area under this curve here, it's just two separate integrals. So this one is not so bad at all. We have the integral from 0 to 4, and this is under our function the square root of x, or x to the power of 1/2. Dx plus the integral from 4 to 8 of negative 1/2 x plus 4 dx. Okay, so anyway, that's just kind of a unique kind of setup for this one. Okay, so last one here, number 5. Example 5, set up but do not integrate integrals for the total area of the regions located between the two curves shown. You may use a calculator, and they give us f of x and they give us g of x. Now, here is kind of what's interesting. One is they don't label this graph, so you have to know by function identification which function is which, or you can go ahead and graph it. And I want to show you just by looking at this. Notice how this is a cubic function for our function f. Oh my gosh. Notice how this is a cubic function, x cubed. Okay, so I would expect that to be this function here. And so f is on top here, and then it's on bottom. Okay, and so that's important to note. And then we have g of x, and that's a negative quadratic. Okay, so notice how g is here. It's a quadratic function. It's on bottom, and then it gets to the top of f. Okay, and so they kind of switch. Our integration switches here. The other thing that I don't have is I don't have these bounds. I need to know where x cubed minus x squared is, and I'm going to set this equal to negative x squared plus 4.1x. Okay, and so I'll use calculator for this one. This one is calculator active, so we can graph our two functions. And here's the other way, right, that you would know which function is which. We have negative x squared plus 4.1x. Okay, and so you can kind of see that. I'm gonna adjust my window here. Let's go -3 to 3, and that's kind of better. We can zoom out a little bit here. Okay. So, bounds, where are they equal? Well, they're equal here at negative 2.025, x equals 0, and at x equals 2.025 again. Okay, there's our upper bound. So, we can go ahead. They say set up, but do not integrate. So that's another key thing that they ask us to do sometimes. They say, what's the setup? And you can save yourself a lot of time. So this is going to be the integral from, I have negative 2.025 to 0. And for this one, f is on top. So it's going to be f of x minus g of x dx. Okay. Plus the integral, or the area, from 0 to positive 2.025. And this one, g of x is on top, so it's g minus f. Okay, dx. All right, so on this one, we had to go ahead and use a calculator to find those exact bounds. That's super nasty. Don't try to solve that. But but use your calculator when you have access to it, okay? So anyway, area between two curves. You're going to integrate the area of the top minus the bottom. So integrate top minus bottom curve. If you have it in terms of y, right minus left, that's super, super rare, but top minus bottom will definitely be on the AP test. If you learned something, give the video a thumbs up. I'll see you in the next video.